Hi, and welcome to our lesson 6.6. Our topic today is vectors, not just geometric vectors, but also algebraic. You can see that we're going to look at some vocabulary about vectors to start today, and I'm going to direct your attention over here. This vector starts at this point, ends at this one. I don't know their names, but I could call this thing vector A, like that. The symbol for vector, it looks like a ray symbol from geometry, but it's missing one of the arrowhead sides, and that's intentional. Our textbook also uses a boldface notation. I have a hard time with bold with my pen, okay, so I'll probably use the vector with the symbol. So we could call this vector the vector MN. We start with its initial point. Note that that's the one that doesn't have the arrowhead on it. The initial point. The terminal point in this one is point N. And we always name starting with the initial point, which just makes sense. A vector really is no more than a directed distance. Directed distance. And you could think of it as a line segment that's got a direction and it's a certain length. The magnitude of a vector is its length, or size, if you will. In terms of naming conventions, if we want to talk about the magnitude of a vector, we put it in double. It looks like absolute value, only it's 2 bars on either side. So if you see that, we're talking about the magnitude or the size of vector A there. OP over here is a vector in standard position. That's a vector whose initial point is on the origin. And the direction of that vector is the angle right here. I'm going to call it theta. The direction is the angle that the vector makes with the positive x-axis. And I say x-axis, but really not all vectors have to be at the origin. In standard position, it's easy to say x-axis, but really it's the angle that the vector makes with the horizontal. All right. We're going to, again, in the vocabulary genre, talk about equal vectors. In order to be equal, 2 vectors have to have exactly the same magnitude and direction. So they have to be exactly as long as each other, and they have to be going the same way. Opposite vectors have the same magnitude, but they go in exactly opposite directions. So the same magnitude but opposite directions, and by that we mean that they go in 180 degrees difference from each other. Opposite direction. And if you think about that for just a minute, this vector and this are opposite because they have the same size, but they're going in opposite directions. That has to do with it's 180 degree difference in direction. Alright, to be parallel, 2 vectors just must be going, just like line segments, they must be going in the same direction. So they have to have the same direction. And we've got some vectors to play with on the following screen. Vectors A, B, C, and D here, and E as well. We're going to answer some questions using those vectors. It says that we should name a pair of equal vectors, And in order to be equal, you have to be going exactly the same direction, and you have to have the same size. And the only two that I see that look like they might fit that bill are vectors A and C. Opposite vectors, exactly opposite directions, and same length. And I know that you see them up there. Vector B and vector D. We're naming all the parallel vectors, and I would remind you that parallel vectors have to be going exactly in the same direction. And I would ask you to think, how many pairs of vectors do you see there that are going exactly in the same direction? I hope that you're saying only one, okay? Because vectors A and C are parallel. They both start and go up to the northeast. It's not true that B and D are parallel. They're 100 degrees going opposite directions. They're not parallel. That E is not going in the same direction as either A or C, so E can't be part of any parallel pair either. Only one pair of parallel vectors there, folks. Alright, vectors can be multiplied by a scalar, which is just a number, a constant. And the challenge next is to use a ruler and a protractor to get twice the vector A here. So what we're going to have to do is multiply or find the length of vector A and duplicate its length. We got to double it, and then we'll also have to have that angle. So I guess I should get my math tools out. Alright, let's measure that vector. It appears to be about 32 units long. So I need 32 times 2 because I want to get twice that. Mine's going to have to be 64 long. And it has to follow the same degree, the same angle that this does. And you can see my ruler also is telling me the angle. And so I am going to use that factoid to my advantage. I did not turn mine at all, so I have the same angle that I did up there, and I just need to go twice as far. So I got a 64, and that's pretty close. Not perfect, because we never get perfect, but I believe that this is really close to being twice the vector A. Alright, the next topic that we need to talk about are adding vectors. And it is very important that we introduce you to the term that is the sum of two or more vectors. That is called the resultant. So when you see the term resultant, that means that we're thinking about two vectors that were added. There are two different methods for adding two vectors. They should come up with the same result, and I'd like to show you both ways. The parallelogram method is exactly what it sounds like. What you try to do, as close as you can get, you want to duplicate or make this into a parallelogram. So let me turn so I get the angle right there, and see that one is about 42. So I want to come up here keeping that same angle, and I want to draw along here 42, which is right about there. Then I'm going to complete the parallelogram. I need to get the length of this part. That looks right to be about 16. Let's get that distance duplicated over here. Here's our parallelogram. Now, the resultant is not either of those lines that we drew. Instead, the resultant, the junction where both vectors started and then connected to where they intersect over here. So I'm going to draw now the resultant, and as long as I've got my tool here, I'm going to measure that as closely as I can. I want to get to 0 degrees because that will be the horizontal. And from the horizontal. We want to measure the angle. So here I need to draw another segment because our direction is always measured based on the horizontal. And now I'm going to come up here and there we go. Our angle is 38 degrees, and I'm reading that from my ruler that does both things. And our resultant in this case is really close to 40. It looks like 41. So it looks like our vector is around 41 units at 38 degrees. All right, now we want to do this a different way. This is called the tip to tail method, or the triangle method. And really, folks, this is much easier. The two vectors are lined up so that the end of one of them, the tail of one, is at the tip of the other, the start of the other. And to get the resultant here, what we do is just connect from the initial point of the first vector to the terminal point of the second. And let's get back in some color so that we can see what we're doing here. Yeah, it looks like it's about 41, so we've got that part nailed. Let's check that angle out. Let's see, it was, oh, look at that, 39. Yeah, pretty darn close. Here's the horizontal. And that angle measures right around 39 degrees. Measuring with implements is never going to be precise or as accurate as you want it to be. However, both of those methods work for adding two vectors geometrically. I would guesstimate that this is the more the one that's easier to use. At least that would be my guess. Okay, now it says that we should find the horizontal and vertical components of this resultant. And folks, you have part of that. You have an angle, and I'm going to go with this 39-degree angle here. If we want to take the vertical and horizontal parts of this resultant, then we want to investigate, remember 39 degrees and 41 units in length. We want to find out how far it is in the vertical direction, how far it is in the horizontal direction. You guys, that looks like SOHCAHTOA trig to me. The horizontal component we would find by taking the cosine of our angle, 39, equals horizontal over hypotenuse, 41, or you could think the horizontal component is going to be the cosine of the angle times the length or magnitude of the vector. So 41 times the cosine of 39. Okay, I have my calculator and it's set to degree mode since I'm entering an angle that I figured in degrees. I need 41 times the cosine of 39. And in the horizontal direction, that distance is real close to being 31.9 units. In the vertical direction, you guessed it, it's going to be the sine, because sine goes with up and down. So sine 39 is V over 41, and V is going to equal 41 times the sine of 39. 41 sine 39, and we're talking right around 25.8 units for the horizontal component. Okay, and again, to do this, what we did was box in a right triangle between our resultant and the horizontal. We know the angle, or we can find the angle. We said vertical stuff goes with sine, horizontal stuff goes with cosine, and we went from there. Very good. I'm going to go ahead and get rid of my ruler now, because instead of geometric, we're going to focus on the algebraic vector from here on out. The ordered pair, and notice that it's brackets, not parentheses here, like little darts. The ordered pair HV is used to represent a vector whose horizontal component is H, and whose vertical component is V. So we'll get used to seeing this as well. The ordered pair inside the little darts, horizontal, vertical components. And it says that, and I would submit to you that all of these vectors are parallel, and they are all the same length, folks. Using, it says, the label point as the initial point, can you sketch in the right triangle that's represented by a vector with components 3 and 4? Well, I think so, because that's 3 across and that's 4 up. So we're talking horizontal and vertical. Can we find the magnitude of such a vector? Well, sure. We just sketched in a right triangle, and if this is 3 and this is 4, then the hypotenuse is our magnitude, right? That's the distance from the start of the vector to its tip, and it would be 5 because we're in a 3, 4, 5 triangle. So units, 5 units, and we got that because that is, by the way, I guess we should show it the right way. The magnitude of that vector is the square root of its horizontal component plus its vertical component. Okay, that's the distance from start to stop. We're asked next to write the ordered pair that represents a vector MP. I didn't get the vector symbol drawn on there before. If M, now notice we're talking point here because we've got parentheses, not the little dart things. So we want to write the ordered pair that represents this vector from M to P, and then find its magnitude. Well, that vector MP is equal to, now we are using darts, because to get from here to here, P is the end, so we're going to subtract -3 minus 2, -5, 4 vertical minus vertical, 4 minus -1, which is 5. There's the vector that is MP. That would be starting at 2 and going to 1, and then P would be -3, 4. Down here. Yeah. Alright, so we have the vector in its horizontal and vertical component form. We need its magnitude. The magnitude of that vector is going to be the square root of 5 squared plus -5 squared. 25 and 25 is 50, so it's the square root of 50. That's 25 times 2. That makes it 5 root 2. The magnitude of that vector is 5 root 2. We're asked next just to find the magnitude of this vector, and I would submit to you folks that that is also a Pythagorean triple. Some of you might recall it, but if you don't, we're going to square the horizontal component, square the vertical component, whoops, add and then take the square root, and you should get 25 there. It's a 7, 24, 25 triangle. Okay, good. Let's continue on in talking about these algebraic vectors, and we'll look at some operations that you can do with vectors. For two vectors it says described as, and vector M has A and B as its horizontal and vertical components. Vector N here, you can add two vectors, and the way to accomplish that is to add horizontal to horizontal, A plus C, add vertical to vertical. So algebraically, what we're doing is, we did it geometrically at the start, now we're algebraically. You can add the horizontal and vertical components of both. Subtraction is also defined for vectors. M minus N means that we start here. So we are A minus C and B minus D. That is horizontal minus horizontal, vertical minus vertical. Scalar multiplication is also defined, so if I'm going to multiply vector M by this K, then what I'm multiplying is A and B, so I am going to have an end result of KA, KB. Adding, subtracting, multiplying are all supported with vectors. Now we have some example problems. We're asking you to do 4 little vector ops here, and I would say this would be a good time to pause and see if you and I get the same thing. Okay, I'm going to go ahead here. Adding U and V, I add the horizontal components of each. And 1 plus 0 is 1. I add the vertical components. Negative 4 plus 8 is 4. Now I'm subtracting the vector U minus V. So this one minus this one. 1 minus 0 is 1. Negative 4 minus 8 is negative 12. 1/2 V, that's multiplying 1/2 times the horizontal and vertical components here, and half of 0 is still 0. Half of 8 is 4. Finally, the last one, we want to take twice the size of the U1 and add it to 3 times the size of the V vector. So I believe that many of you won't need to show this work, but I want to show it right here. We're doing twice of this, and we're going to add it to 3 of this, just so that we remember what we are doing. 2 times 1 is 2. 2 times negative 4 is negative 8. So after we've done this multiplication first, because it takes precedence over the addition, we got to do this multiplication next. 3 times 0 is 0, and 3 times 8 is 24. Now we can worry about adding together those 2 vectors for a final result. 2 and negative 8 plus 24, 16. All right, very good. Adding, subtracting, multiplying with vectors. And our final topic of the day, a vector that has a magnitude of 1 is called a unit vector. And you can see that I have 2 unit vectors marked here. In the horizontal direction, a unit vector in the direction of the positive x-axis is represented by I. This does not mean it's an imaginary number. We're using that variable I to represent the length of a unit vector, so a vector that has magnitude 1 that's headed east. The vector that is headed north here is a J vector, and those are both always shown in cursive lowercase letters. Any vector, okay, can be represented, and there should be a symbol right there. Any vector can be represented as a sum of unit vectors. For example, vector M could also be represented as A times I. That's the horizontal component times 1, right? Because 1 in the unit is a unit vector there. I is a unit vector added to B times J. Another way to represent this vector M is as a sum of unit vectors. A units in the east direction, B units in the north direction. This says that we should find the magnitude of this vector and then write it as a sum of unit vectors. So 2 different things here. I'm going to call it vector V since it didn't have a name. And to find its magnitude, I'll remind you that that's a Pythagorean theorem. 8 squared plus negative 6 squared. 64 and 36 is 100. We want the square root of 100, or 10 is its magnitude. To write that vector as the sum of unit vectors, we would say that it has 8 in the horizontal direction, plus it has, well, I guess we could say plus it has negative 6 in the j direction. And of course, if you wrote that as 8i minus 6j, it'd be the same thing, mean the same thing. So we just had some vocabulary today really about vectors and a tiny bit of math. The magnitude is you use the Pythagorean theorem on the horizontal and vertical components. One thing that folks have had trouble with in the past is this topic, where we're going from a set of 2 points to a vector. And I would just remind you that if we're doing vector MP, it's this minus this, because the direction is important here. So I'm going to put a star there and say remember that in class tomorrow. I hope that you'll get out there and do that U-try just as quick as you can, and I'll see you in school.